So one of the first things we learned in Unit 2 is that this limit, the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, this limit we've seen so many times it actually represents the derivative. And we can use this limit to figure out a bunch of the derivative formulas we use throughout all of calculus. So I'm going to show you how we figure out one of those formulas using this limit today, but if you ever wanted to figure out all the other ones, you could use the same process with this limit. Okay, so I have a table over here now of things we want to find the derivative of, and then we're going to see if finding the derivative using this limit, it will show us a bit of a pattern that we can use to make a formula out of. So the first thing we're going to do is just find the derivative of x squared using this limit. So we're just going to plug in x squared. So it'll be the limit as delta x approaches 0 of x plus delta x squared. That's our f of x plus delta x term. Then we will subtract f of x, so we will minus x squared. And then it will still just be over delta x. Now to simplify this, we're going to expand this squared term right here. So we will have the limit as delta x approaches 0 of x squared plus 2x delta x plus delta x squared. And then bring down this minus x squared, and it is still all over delta x. Now, two things we're going to do in this stage. We're going to notice that we have an x squared and a minus x squared. So both of these terms just go bye-bye. They cancel. And with these two terms left, our 2x delta x and our delta x squared, we can notice both of them have a delta x in them. So we can factor that out. So it's going to turn into the limit as delta x approaches 0. We're going to factor out that delta x, and what's left is 2x plus delta x. And then it's still all over delta x. But because it's all over delta x, and we have this delta x we factored out in the numerator, we can cancel those. And then we are just going to be left with the limit as delta x approaches 0 of 2x plus delta x. At this point, we can direct substitute, and we will get just 2x. And that is going to be our answer. So plugging in x squared to this limit, we get 2x, which basically means the derivative of x squared is 2x. So I'm going to write this over here. Now with just one example where the derivative of x squared is 2x, we can't really make a formula out of that. So we're going to keep going. So this time we're going to find the derivative of x cubed using this limit. So we have the limit of delta x approaching 0 of x plus delta x all cubed. That's our f of x plus delta x. Then minus f of x means we're going to subtract x cubed. And then it's still all over delta x. Now at this point we're going to have some not as neat expanding to do, where we expand this cube term. So expanding that, we will get x cubed plus 3x squared delta x plus 3x delta x squared. And then we'll add delta x cubed. And then now we're just going to bring down this minus x cubed. And then it's still, again, all over delta x. And at this point, we do kind of the same thing. We notice there's an x cubed and a minus x cubed. So those terms go bye-bye. And in this case, we're just going to notice that, oh, all the terms have a delta x in them again. So we're going to factor that out once more. So now we'll have the limit of delta x approaches 0. We have that delta x we factored out. And what remains is 3x squared plus 3x delta x plus delta x squared. And that's all over delta x. So now if we cancel these delta x's and then we direct substitute, we're just going to get 3x squared, and that will be our answer for the derivative of x cubed. Okay, so I went ahead and spared you the time of me doing that same process with x cubed, x squared, x cubed, x fourth, and x to the fifth. But I have all the answers here for you. So derivative of x squared is 2x. Derivative of x cubed is 3x squared. Derivative of x to the fourth is 4x cubed. And derivative of x to the fifth is 5x to the fourth. And we can notice a bit of a pattern here. So when we have x squared, that's x to the power of 2, we notice that this 2 just drops down to multiply in front as a constant. If we have x cubed, this 3 drops down to multiply in the front as a constant. Same happens to x fourth, and same happens to x to the fifth. So let's say we were differentiating, trying to find the derivative of x to the n. The first thing we can do, if we're going to differentiate this, is notice, because the power always drops down to the front, we know the derivative is going to be n times x. But what is the power of x? So if we look over here, derivative of x squared is, in terms of just the power of x, x turns into a first power. So let's just write a 1 right there. If x was the power of 3, the power of x turns to a power of 2. X is power 4, x turns to the power of 3, and x is power 5, x turns to a power of 4. So x is just subtracting 1 to their power, so that means if we were to go back to this example, deriving x to the n, the power of x after we differentiate will be n minus 1, because it's 1 less than before. So that means if we were to derive x to the n, our answer will be nx to the n minus 1. And this is our first main very important derivative formula, and we call this the power rule. Okay, so we have this same thing. Derivative of x to the n is nx to the n minus 1. But what do we actually write in terms of notation to show that this is the main function and this is the derivative? Well, one way we can do it is just call our original function f of x. So f of x equals this. But how do we write that this function down here is the derivative? Well, we write f of x again, but in between the f and that parentheses, we're going to do a small dash like that. And that stands for f prime of x. And f prime of x means it's the derivative of f of x. So as I said, f of x is the function and f prime of x is the derivative. And we can actually keep going with this. If we wanted to take the derivative of the derivative, that would be called the second derivative. But in terms of writing it, we just write 2 dashes, and we will just call it f double prime of x. And this process actually can keep going. We can have f triple prime of x, or like f 1 million prime of x. But after we get past the third derivative, once we start writing after that, we would have to write 4 dashes, 5 dashes, and that's way too many. So let's say we wanted to take the 7th derivative or something, or anything above 3, we wouldn't do dashes anymore. We'd actually just write a number. So like if I was doing the 7th derivative, as I said, we'd just do f and then a small 7 and then of x. And we could actually do this with other variables. So we also know like some functions are like y equals. Now with y, there are a few things you could do. You can write y as your function and then y prime as your derivative. Or another really common way of seeing it is instead of y prime, it would be dy dx is how we write it. So if y was our function, dy dx is our derivative. And if we were to keep going with second derivative, third derivative, all of that stuff, it would look like this. So we'd still have dy dx, but there's going to be squares. So we would write d squared y dx squared. And that's really weird notation, and I still don't know why we do it like this, but I just know that that's how it works. And so if you see d squared y dx squared, just know that means the second derivative of y. Okay, so I'm going to show you a few examples while also showing you some new formulas using this. So we know f of x equals x squared. Take the derivative. If we use that same formula, we're going to get f prime of x equals 2x. We have something slightly harder because the numbers are bigger. If we had f of x equals x to the power of 7, then f prime of x, using this formula, would be 7x to the power of 6. Now here's a little curveball. What if f of x was to equal 2x cubed? Now it looks different this time. We have an actual constant value up in front before our x to a power of whatever term. In this case, x to the power of 3. And when you have a constant out front of, like in front of your variable multiplying there, you're just going to ignore it and you're going to multiply it with the derivative. So pretend this isn't here first. Let's take the derivative of x cubed. The derivative of x cubed using our formula is going to equal 3x squared. And now we have to remember this constant, and what we're going to do, we're just going to multiply our derivative by that constant. And so the derivative of 2x cubed is going to be 3x squared times 2, which is the same as 6x squared. So if we wanted to generalize this formula, it would be f of x equals a x to the n, where a is going to be that constant out front. Then f prime of x would equal a n x to the n minus 1. It's exactly the same as this one we have here, except we would just have an a out front of both the original function and the derivative. And here's a special case for you. It's still using the same formula, but it's kind of a special thing you could just memorize and see on site. Let's say f of x was to equal x. In this case, f prime of x would equal 1, and here's why. So x is just x to the 1. So if we use this formula, it would be, so x to the n, so n in this case is 1. So we bring the n out to the front, so it's just 1, multiplied by x to the n minus 1. So x to the n, in this case it's 1, minus 1. That's the same as 1 times x to the 0. X to the 0, anything to the 0 power is 1, so that's just going to be the same as 1 times 1, and our answer is just going to be 1, and that's how we got this answer. Now before we move on, there's another important thing I really have to show you guys, and let's say f of x was to just equal a number, in this case 5. Now there's no x terms here at all, so when it's just the derivative of a constant on its own, we're not going to just bring it down. If it's a constant on its own, the derivative is always going to be 0. So f of x equals 5, f prime x equals 0. Or in this case, f of x equals 1, 2, 3, 4, 5, 6, 7, 8, 9. F prime x is still going to equal 0. And even in this case, f of x equals pi e. But just notice, pi and e are both constants. Even though they're really weird constants, they're still just constants. So the derivative of that is just going to equal 0. So the thing to remember, if you derive a constant on its own, it's always going to be 0. Okay, this next part looks a bit overwhelming, but I'm going to do my best to explain all this to you. So the next 6 derivatives we need to know are the derivatives of the 6 trig functions. And these ones, it just looks like a bunch of trig. And it really is, but there are a few memory tips that I can help you to help you try and remember all these trig derivatives. So let me explain what they all are first. So f of x equals sine x, f prime x equals cosine x. If f of x equals cosine x, f prime x equals negative sine x. If we derive tangent, we get secant squared. If we derive cotangent, we get negative cosecant squared. If we derive secant, we get secant x tangent x. And if we derive cosecant x, we get negative cosecant x cotangent x. And so there's a few things that I'm going to write over here that will hopefully help you remember these easier. So the first thing is that a bunch of these derivatives or trig functions are friends. So with derivatives, sine and cosine are friends. Notice that if you derive sine, you get cosine. You derive cosine, you get negative sine. I know there's a negative sign difference here, but it's still just sines and cosines. So those are friends. The other thing, tangent and secant are friends. As you can see, derive tangent, you get secant squared. If you derive secant, you get secant tangent. So always secants and tangents. And lastly, the last 2 trig functions, cotangent and cosecant, are friends. You derive cotangent, you get negative cosecant squared. You derive cosecant, you get negative cosecant cotangent. So the first thing you really need to know is that all these 3 pairs of best friends with trig in terms of derivatives, and that will help you start to remember a few things. And there's a few other tips. So notice if f of x equals a trig function that starts with so like cotangent, cosine, cosecant, then that means f prime x is always going to start with a negative. So notice, we derive cosine, we get negative sine. If we derive cotangent, we get negative cosecant squared. And if we derive cosecant, we get negative cosecant cotangent. So that's another thing we have to know. And there are 2 more kinds of things. So notice that if we derive tangent or cotangent, then both of their derivatives are going to be squared. And so if we remember that the derivatives are squared, and we also remember these rules about which trig functions are friends, then we could figure out what the derivative is. And so lastly, we will focus on the secant and cosecant kinds of relationship. And so whether you derive secant or cosecant, that original trig function will be in the same answer, or in the derivative, in your answer. So you derive secant, derivative is secant tangent. So as I said, the function will be in its answer. So there's secant in the derivative and in the function. Same with cosecant. F of x equals cosecant x, f prime x equals negative cosecant cotangent x. Both of them have cosecant. And they're multiplied by their friend, basically. So with secant and cosecant, their derivative is going to be themselves multiplied by their best friend. Okay, so in short, I'm going to go over these tips again, the memory tips for these derivatives. So remember that sine and cosine are best friends, tangent and secant are best friends, and cotangent and cosecant are best friends. Also remember the derivative of any of the functions that start with so cosine, cosecant, and cotangent, those will always start with a negative symbol. And the derivative of tangent or cotangent, that's going to be that will be their friend, and then it will be squared. So tangent is going to be secant squared, and cotangent is cosecant squared, or negative cosecant squared. And lastly, the derivative of secant or cosecant, it's going to be themselves times their friend. Also, taking into account the rule that derivative of the cofunctions are going to be negative. Okay, so what if we had something like this? F of x equals x sine x. Well, this doesn't look too bad. We do this formula, so if we had x, check this formula up here, it's an x to the n thing. So derive x, we get 1. And then let's derive sine x now. Derive sine x, we get cosine x. So our answer is 1 times cosine x, which is just cosine x. So that means that's our answer for the derivative of x sine x, right? And no, that is actually completely wrong. And here's why. So if we look, the f of x equals x sine x. This is x times sine x. And the thing I have to introduce to you is that we can only take derivatives if they are, like terms are added. So if it was f of x equals x plus sine x, then our answer would pretty much be right. F prime of x would equal 1 plus cosine x. But our terms here are multiplied. And we actually can take this derivative, but it will have to be a new rule I have yet to teach you. So this is going to be called the product rule. So in this case, I'm just going to do, let's say, y equals f of x multiplied by g of x. I'm just going to go show you straight immediately what the formula is. So take the derivative would be dy dx. Remember, that's notation I showed you earlier. And if we wanted to derive f of x times g of x, it will be f prime of x times g of x plus f of x times g of x, or times g prime of x, my bad. So this looks like a bunch of letters and stuff, but here's what it means. So basically you take the derivative of the first and you multiply by the second function. And then you add, taking the derivative of the second function, multiplying by the first function. That's what all this notation basically means. So let me show you a few examples using this new rule. Okay, let's start off now with this first derivative that I did completely wrong earlier. F of x equals x sine x. And let's see if we could use the product rule to do it right. So the first thing we're going to want to do before we actually derive is identify what these two terms are. So the first term is x, and the second term is sine x. So now that we know that, we can use our product rule. So product rule says take the derivative of the first, so the first is x, derivative of that is 1, and multiply by the second, just on its own. So multiplying by the second means to multiply by sine x. Now we're going to add multiplying by the first, just on its own, so x, and multiply by the derivative of the second. So derive sine x, we get cosine x. And that's going to be our derivative. We could simplify this 1 times sine x turns to just sine x. So f prime x equals sine x plus x cosine x. Okay, so let's try another example. This time f of x equals x squared tangent x. So before we start, can you see what the two terms are? I'll give you a second. Okay, so the first term is x squared, and the second term is tangent of x. So now using our product rule, it says to derive the first function. So derivative of x squared is 2x. And then multiply by the second function. So multiply by tangent x. Then we add the first function on its own. So that'll be x squared. And then you multiply by the derivative of the second function. Derivative of tangent x is secant squared x. And then this is just our answer. So f prime x will equal 2x tangent x plus x squared secant squared x. Okay, there is one more formula we learned in Unit 2, Lesson 1, and that is going to be called the quotient rule. So what if we had y equals f of x over g of x? So in order to solve this, our new formula is going to be f prime of x times g of x minus g prime of x f of x all over g of x quantity squared. So this looks a lot uglier than the product rule, and it really is, but it's actually very similar to the product rule if you look at it. So notice in the product rule, we multiply the derivative of the first function by the second function. That's the same in the quotient rule. You multiply the derivative of the first function times the second function. In the product rule, we were to add after that the first function multiplied by the derivative of the second function. That's the same thing here in the quotient rule. The first function times the derivative of the second function. The only difference is instead of adding these two things together, in this case we're going to subtract. So we do derivative of the first times the second, and then minus derivative of the second times the first. And then just for some reason we have to divide by the second function squared, but that's just there for some reason, just got to memorize that. So this is probably one of the worst to actually try and memorize. So a bunch of the higher level people in calculus, they actually thought of a weird way to remember this. And what they say is low d high minus high d low over low low. And so that sounds really weird, but here's where it comes from. It's low, which means the bottom, d high, which means the derivative of high. So low is bottom, and then high is the top function. So low d high, because it's the low, like the set bottom function, times the derivative of the top. And then it's minus high, because it's just a normal top function. And then d low, because you have the derivative of the bottom function. And then all over low low, because you multiply or you divide by the denominator squared. So low times low. It's really weird, but if that helps you, I'm just putting it out there for you. Okay, I'm going to give you two examples with a quotient rule now. So let's say f of x was to equal x over sine x. So in this case, we're going to use the quotient rule. Now first, I'd say quotient rule, it's a lot easier to identify what the two functions are, because the first function is just the numerator, and the second function is just the denominator. So we don't really have to spend work identifying those. So let's just invoke the quotient rule now. So it's derivative of the top times the bottom minus derivative of the bottom times the top, and then it's all over the bottom squared. And we can simplify this a bit. 1 times sine x is sine x. X times cosine x is just x cosine x. And then it's all over the denominator squared, so all over sine x squared. And that is our answer for that derivative. Okay, let's have a bit more fun with some more interesting terms. So f of x equals cotangent x over x cubed. So taking the derivative of this, we're going to first take the derivative of cotangent x, which we know is going to be negative cosecant squared x. And then multiply by the bottom, so multiply by x cubed. We're going to subtract derivative of the bottom, so that's going to be 3x squared. Multiply by the top, all over the bottom squared. Simplifying this one, this is going to turn into negative x cubed cosecant squared x. And then over here, it's just still going to just be minus 3x squared cotangent x. And this denominator x cubed all squared turns into x to the 6th. And this one you can actually simplify a bit more. So notice that there is an x squared in both of these. So what we could do, there's also a negative sign in both of these. So we could factor out a negative x squared. And that will just leave us cosecant squared x. And then plus this time, cotangent x. Or plus 3 cotangent x. I forgot, there's a 3 right here. So don't forget that. That's all over x to the 6th. And so now this x squared can cancel with this x to the 6th. That x to the 6th turns into an x to the 4th in the bottom. So let's just bring the answer up here for some reason because we're out of room. And so our final answer would be negative times cosecant squared x plus 3 cotangent x all over x to the 4th. So quotient rule, you get really ugly answers, but it works out, helps you take the derivative. Okay, so also in Unit 1, we learn a few really basic applications of derivatives. So here we have an example problem here. Write a tangent line to f of x when f of x equals x squared plus 2x plus 5, when x equals 2 and y equals 13. So if you remember, a tangent line to a function, this looks like a parabola, so it's going to look like this. And a tangent line is going to look something like this. It's going to be a straight line that only touches the graph at one point. It's a really crude drawing, whatever, but you get the point. It touches whatever your graph is at one singular point. So because of that, there are going to be two things that we need to know for a tangent line. We're going to need to have that one point where they intersect, and we're going to have the slope at that one point. And so a thing to know is that the derivative, as I believe we've said this before in class, but the derivative is the slope of the function at any point. So like the derivative can be a function. So if you plug in a number to that function, then you will get the slope at a specific point. So because the derivative is the slope at any point, if we had the slope at a single point, and we also knew what that point was, we can write a tangent line for that exact spot, because we'll know it will cross at this one point. That will be the point we use to write our tangent line, and we will have the same exact slope as the function on that one point. So let's figure this out. How do we do that? Well, we're actually given our one point here, thankfully. X is 2 and y is 13. So we have our point, but now we have to find what our slope is. And I said a moment ago that the derivative is going to be able to give us the slope. So let's derive this function. So f of x equals x squared plus 2x plus 5. That would mean f prime x equals... Okay, the jump cuts because I originally made a mistake, but here it is. So we derive f of x equals x squared plus 2x plus 5. That'll make f prime of x, the derivative, equal to 2x plus 2. And then if you want to, you could say plus 0. And that's a terrible plus. And that's because we're first using power rule on both the x squared and 2x. That's where we get 2x plus 2. And then as I said before, if you're just adding and you're deriving a constant on its own, you get 0. So let's just erase this 0. We don't really need it. And so we have our function for our derivative. So if we plug in this specific point to our derivative, we will have our slope at that point, and we could write our tangent line. So we will take f prime of 2, because 2 is our x coordinate here, and that's going to equal 2 times 2 plus 2. And simplifying that, that's 4 plus 2, and that's equal to 6. So we have our point is 2, comma 13, and that our derivative is equal to 6. So with that, now that we have our point and that our derivative, or not our derivative, our slope is 16, we can write our tangent line. And the form we write a tangent line is y minus b equals m times x minus a. And this is going to be where m is our slope, a is our x value, and b is our y value. Like this. So if we were to actually write a tangent line in that format with our given information, it will be y minus 13, because y minus b, equals 6, because our slope is 6, multiplied by x minus 2, because our x point is 2. And that is our tangent line. Okay, now we have a really similar question, but it's a bit more complicated. So this one is write a tangent line and a normal line to f of x equals 3x cubed plus 7x squared plus 5x plus 3 when x is equal to 1. So analyzing this, we're going to write a tangent line again. That's the exact same thing we just did, so that shouldn't be bad. But also a normal line. And so a normal line we don't use as much, but a tangent line and normal line are the same thing, except they have opposite reciprocal slopes. So say the slope for our tangent line was 5. If we were to write a normal line to this tangent line, then the slope would equal negative 1/5, opposite reciprocal. So that's the first thing we need to know about. The next thing is that, notice, we're only given our x value for our point. We're not given a y value. So what we're going to have to do first is we're going to have to actually just plug in 1 to f of x. So f of 1 is going to equal 3 times 1 cubed plus 7 times 1 squared plus 5 times 1 and plus 3. It's going to give us 3 plus 7 plus 5 plus 3, and that's going to equal 18. So that means we know x equals 1 over here, and we just found out that y equals 18. So now all that's left is to actually find our slope. So to do that, just like last time, we're first going to find our derivative. So f prime x is going to equal, we're going to do power rule for this one, so that's going to be 9x squared. Forgot the equal sign. Let me write that. F prime x equals 9x squared. And then power rule again, plus 14x. That x looks like a plus sign. Okay, and then plus derivative of 5x is again power rule, that's plus 5. And derivative of 3 is just 0, so we're just going to leave that off. So now we have our function for our derivative, and if we plug in x equals 1, we'll be able to get our slope. So f prime of 1 again is going to be 9 times 1 squared, plus 14 times 1, plus 5. This is going to equal 9 plus 14 plus 5, and that is going to equal 28, I believe, if I did that right in my head. Yeah, 28. So our slope is 28, our x value is 1, and our y value is 18. So let's start to write our tangent and normal lines here. So to write the tangent line and normal line, they're going to be the same way. It's y minus this value multiplied by, and then we have our slope times x minus our x value. So first, our y value is 18, so you could write 18 in these spots. Our x value is 1, so we could write 1 in these spots. Remember this format I showed you guys how we got it earlier, whatever. And now we have our slope. So let's say this one, the top one is our tangent line. And we can just write the slope right there as it is. Now for our normal line, we're going to have to do slightly bit different. It's going to be the opposite reciprocal, as I said. So in this case, it would be negative 1 over 28. And that's going to be our slope for our normal line. So let's just write it here. This is our tan line. And this is our normal line. And those are our two lines that we need for our answer. So that's how we find tangent lines and normal lines when we're given a function and a point. Okay, we have another curved ball here. So write a tangent line, typically easy, to f of x equals x squared over 2 plus 5x plus 1,736 when f prime of x equals 7. So first off, don't let this constant scare you. When we end up taking the derivative of that, it's just going to equal 0 because it's a constant. So that's the first thing we want to care about. But also notice, we're not given a point this time. We're given what the derivative equals. So when the derivative equals 7. So in this case, I'm going to show you what we're supposed to do. We're supposed to first take the derivative of the first function so we can get our derivative function itself. So f of x equals this mess. So f prime of x. Now this is x squared over 2. And you see that division symbol, you might think, oh, quotient rule. Don't do quotient rule with x squared over 2. X squared over 2 is the same as 1/2 times x squared. And we know 1/2 is a constant. So with constants, we just take the derivative and then multiply by the constant. So that's how we're going to want to treat this. So the derivative of x squared is 2x, but then we just multiply by 1/2, and those 2's cancel. And so our answer to deriving x squared over 2 is just going to equal x. Now if we derive 5x, we're just going to get 5. And as I said before, deriving 1,736, it's just a constant, so that's going to be 0. So now we have our derivative function. And so remember, we're given when f prime x equals 7. So it says f prime x equals 7, so let's just plug 7 in for f prime x. So 7 equals x plus 5. We subtract 5 on both sides. That will give us 2 equals x. And oh, now we have an x coordinate. Now that we have our x coordinate, we can plug this back into our original function, and we can get a y coordinate. So if we were to plug in for f of 2 now, that would give us 2 squared over 2 plus 5 times 2 plus 1,736. So simplifying this, 2 squared is 4 divided by 2 is 2, plus 5 times 2 is 10, plus 1736. So this bit is just 12, and so 12 plus 1736 is going to give us 1,748. So it's not exactly a nice constant, but it works. So this is what our y is equal to. And this is our x, and then we are given our slope up here. So now we can write our tangent line. We do y minus our y value, which is 1,748, equals our slope, which is 7, multiplied the quantity x minus our x coordinate, so x minus 2. And that is our tangent line. I didn't realize when I was making this problem that a constant would be kind of weird in our y value, but just don't be scared of crazy constants if you're just deriving them on their own. Derivative of a constant is always going to be 0. That's what I intended with this problem. Okay, here's the next one. Write equations of all lines tangent to f of x equals x cubed plus 2 and parallel to y equals 3x minus 4. So what we first want to notice is that we're going to write tangent lines to this function here. But we're not given any x values, and we're not given any slope. However, we're also given this information. The lines have to be parallel to y equals 3x minus 4. Now, when lines are parallel, they never cross. And because they never cross, that means they have the same exact slope. So because they have the same slope, that means that we just have to find the slope of this line, and then that's going to be our slope. And we can do that same process we did with the last problem, where we used the slope to calculate x and y values with that original function. So what we do is we could take the derivative to actually find the slope, But this is just y equals mx plus b. We learned this in like 7th grade. We know that the slope is 3. So let's just go with that. Slope equals 3. M is 3. So let's keep that in mind for now. And next we're going to take the derivative of this function. So f of x equals x cubed plus 2. F prime of x, just power rule, equals 3x squared. Now we know slope is 3, so let's set the derivative equal to 3. So 3 equals 3x squared. Divide 3 both sides, we get 1 equals x squared. And then solve for x. X equals, not 1, x equals plus minus 1. Because we take the square root, we don't know what x is. So x equals plus minus 1. So we're going to have 2 values for x. Because of that, we're going to have multiple tangent lines. We're going to rewrite x equals plus minus 1 up here. And then so now we're going to take f of 1 and f of negative 1. That's just plugging 1 and negative 1 into the original equation. So we can actually solve for what y equals. So plug in 1 here, negative 1 here. 1 cubed is 1 plus 2 equals 3. Negative 1 cubed is negative 1 plus 2 equals 1. And then so these are our y values. So now we can write our tangent lines. Y minus 3 equals 3 times x minus 1. For our other line, we'll have y minus 1 equals 3 times x minus negative 1. So that's actually x plus 1. And that's how we solve for those two tangent lines. Okay, now this problem does not look that nice. So it's find all values of k such that y equals 4x minus 9 is going to be tangent to y equals x squared minus kx. So where do we even start with this? We have we're given the tangent line this time, but we're not given like a slope or a point or anything to actually make it tangent to this function with the value of k. So what are we supposed to do? Now, what we need to realize and think about is like what a tangent line actually means, which I sort of discussed earlier, but let's go over that again. So this looks like a parabola, so it's probably going to look something like this. And tangent line is just going to be a line, as we said before, that crosses, or doesn't cross, it touches this function at one point, only one point. And so that's the first thing we have to notice. They will have the same point. There's at one point on this graph, the function and the tangent line are going to have the same exact point, and at that point only. That's the first thing we have to notice and realize. Now the second thing is at this one specific point, it's going to have the same slope, both the function and the tangent line. So there will be same slope. So we know these two things, but how do we actually apply this to our problem? So the first thing we can think of is that, well, if they have the same point, then that means the two functions are going to be equal to each other at that one spot. Their y values will be equal and their x values will be equal. So if they're the same point, we could set the functions equal to each other. So they're both equal y, so y equals this, y equals this. We get set them equal by y. So x squared minus kx will equal 4x minus 9. This is the first bit of information we'll need for later. We have one equation with us now. Now the next thing is going to be with this same slope stuff. So if they have the same slope, well, we can actually find the slopes of both of these, or not the slopes exactly immediately, but we could find functions for their slopes by taking the derivative, because the derivative represents the slope. So I'm going to erase this, and first what we're going to do is we're going to take the derivative of this function, so that's dy dx, and that's going to equal 2x minus k. Now the reason we do minus k is because k in this case is not treated like a variable. It's treated like some kind of constant value. We just don't know what the constant is yet, but we're treating it like a constant because that's what we're solving for. So the derivative of x squared minus kx is going to be 2x minus k. And this equation up here, y equals 4x minus 9, we can take the derivative of that, but it's just y equals mx plus b. We've seen this forever. We know that the slope of that is going to equal 4. So we have 2x minus k is our first derivative equation. But our other one is that the slope derivative is going to equal 4. So we could just set 4 equal to 2x minus k. As we said before, their slopes are going to be the same. So let's set their two functions, or their two derivatives, equal to each other. And then now, if you notice, we have two equations. And with two equations and two variables, that means we could solve for both variables because we have two equations. And now because this one has a power of 2 in it and this one only has a power of 1, I think the best way to solve this system of equations is going to be by using substitution. So let me get rid of this box I drew here for some reason. And let's isolate k. So if we isolate k, we will get to k equals 2x minus 4. And what we could do is take this and plug it back into this equation. So I'm going to write that up here, k equals 2x minus 4. Now let me clear some space on the board right here. And so let's start rewriting this, but actually plugging in k equals 2x minus 4. So x squared is the same, minus, here's where we're plugging k, so 2x minus 4, multiplied by x, because we had kx, and that's still equal to 4x minus 9. Now if we simplify this, x squared minus, if we distribute this x in here, that will be a 2x squared. And if we distribute the x in here, that will be a minus 4x. And that will still equal 4x minus 9. Now let's distribute this negative into here. That will be x squared minus 2x squared plus 4x, because negative times a negative is a positive, and then equals 4x minus 9. Now if you notice there's a 4x on both sides of the equation, so we could cancel those. This x squared minus 2x squared, if you cancel that, that's just going to turn into a negative x squared. And then we still have this negative 9. So negative x squared equals negative 9. You can get rid of both the negatives by just divide both sides by negative 1. And that will tell us that x equals plus minus 3. So we have x values, but we're solving for k. So what we want to do is plug in the x values to one of our equations. I think this one would actually be a lot easier to plug it into. So let's plug x equals plus minus 3 into here, and then we can solve for k. So it looks like we're going to have two values for k. So we have x equals plus minus 3. Let's plug that into here. So k equals 2x minus 4. If we do it this way, we will have k equals 2 times 3 minus 4. And for our other one, it will be k equals 2 times negative 3 minus 4. Starting on the left side, this will equal 6 minus 4, and this is going to equal 2. So k equals 2. If we go over here, it's going to equal 2 times negative 3 is negative 6. Negative 6 minus 4 will equal negative 10. So our two answers for this equation, or question, whatever, is k equals 2 and k equals negative 10. And that is how we deal with this kind of problem. Okay, so this question is asking us to find all the values where in this function where there's going to have horizontal tangent lines and where there's going to be vertical asymptotes. So for this, what we're going to want to do, we're going to need to use our derivative. So let's just find the derivative first, and then I'll explain how to find the rest of the information. So f of x equals x squared over x plus 1. F prime of x, if you remember our quotient rule, it's going to be derivative of the top, so 2x, times the bottom, x plus 1, minus derivative of the bottom, which is going to be 1, times the top, all over the bottom squared. So that'll be x plus 1 squared. Simplifying that, we will get 2x squared plus 2x minus x squared, all over x plus 1 whole squared. And we can get rid of this 2 by getting rid of this minus x squared. And so we'll just have x squared plus 2x over x plus 1 all squared. And that's going to be our derivative. So let's get rid of all this other stuff. Okay, so now where do we actually find where horizontal tangents and vertical asymptotes are in this? So the important thing to remember is a horizontal tangent, that's just going to be a horizontal line. And what do we know about the slope of a horizontal line? Slope of a horizontal line is 0. And so remember, the derivative represents the slope. So if we set the derivative equal to 0, we could solve for the x values where there will be horizontal tangent lines. So let's set the derivative equal to 0 now. And so notice we have a numerator and denominator in our derivative. The fast track method to remember is that there is only going to be, we only have to care about when the numerator equals 0 for a horizontal tangent. Like if you want to see how that plays out, just multiply both sides by x plus 1 all squared. And so this will, if we multiply by x plus 1 squared, this will cancel. That will just be 1. If we multiply 0 by that, it's just going to be 0. 0 times anything is 0. So we have that. So let me put this back to normal. And so that would mean, by that logic I just said, that means 0 equals x squared plus 2x. And don't subtract 2x to the other side and then divide by x, because x could equal 0. So we don't want to do that. Let's just factor out an x on this side. So it'll be x times x plus 2. and then this is just an easy equation. X will equal 0 and negative 2. So the two x coordinates for when there's horizontal tangent lines is x and negative 2, or x equals 0 and x equals negative 2. Now for the vertical asymptotes, it's going to be very similar. We do need to set the derivative equal to 0. However, instead of the numerator being what we set equal to 0, this time it's going to be the denominator what we set equal to 0. If you remember what we learned when we were learning about continuity, we said that denominator equals 0 is when there's a vertical asymptote. So that's all we're doing here. So denominator equals 0. That means 0 equals x plus 1 all squared. And so just square root both sides. Square root of 0 is 0. Cancel these. That will be 0 equals x plus 1. And then x equals negative 1. So x will equal negative 1 when there's a vertical asymptote. And as we said before, I forgot the actual value. I think it was x equals 0 and x equals negative 2. That is when there will be the horizontal tangent line.